Hi everyone, welcome to May 12th, Unit 8, Lesson 5, Electromagnetism. I'm first going to show you the answers from the worksheet that you were assigned in your packet 4, which hopefully you received in the mail. The title of the worksheet is Magnetism Questions. So if you have not received packet 4 yet in the mail, please email me and let me know, or just know that it should be hopefully coming today. I'm going to show you the answers. So if you did complete it, you can check your work. Number 1 said to list 6 things in your home or classroom that are made of metal that are not magnetic. And so here are some of the suggested answers. Again, you could have different answers as long as, again, they're not magnetic. Number 2, describe some things in nature that are magnetic. And so examples here. You can take a look at the Earth is magnetic because it has a North Pole and a South Pole. So if you're unable to come up with answers, you could, of course, pause this too, just to check your work. And you may have had other answers as well. Number 3, when a magnetic compass points north, is it pointing to the true North Pole of the Earth? Explain. And the answer is no, it's pointing to the magnetic North Pole. The geographic North Pole and the magnetic North Pole are in different places. Number 4, describe how you would build an electromagnet. Wrap copper wire around an iron nail. Connect the copper wire to the positive and negative ends of a battery. The nail wrapped with wire will become a magnet because of the electricity flowing through it. So again, you can check your answers to this lesson that was assigned yesterday. We're going to look at the digital lesson from the book. Again, this is Unit 8, Lesson 5 on Electromagnetism.
Matteo and Imelda have a great media room where they hang out, listen to music, and watch movies. What they don't realize is that the room would be very quiet without electromagnets. Click each highlighted area to see why, and the next arrow to discover more about electromagnetism and its uses. In their media room, Matteo and Imelda have a great surround sound system. Their awesome speakers produce sound because of electromagnets. Matteo and Imelda's mother told them they had to go outside. Since they weren't done watching a movie on Matteo's laptop, they took it out into the yard to finish watching the movie. Matteo's computer uses electromagnets. He couldn't save movies or music to the computer's hard drive without them. Also, Matteo's laptop might overheat if it did not have a cooling fan. The cooling fan's motor turns because of an electromagnet. Imelda prefers listening to music in the media room. But Imelda's cousin, Helena, likes to go out into the yard to listen to music. Helena doesn't want to disturb the neighbors, so she wears headphones. The electromagnets in the headphones help Helena hear the music clearly, but their design also makes sure no one else is disturbed by Helena's music. Welcome to the lesson, Electromagnetism. In this lesson, you'll learn about the relationship between electricity and magnetism. The vocabulary words for this lesson are electromagnetism, solenoid, electromagnet, electric motor, electromagnetic induction, electric generator, and transformer. Imagine a junkyard stacked high with ruined cars. How could someone have moved these cars into stacks when each one weighs thousands of pounds? Electromagnets are tools that can be used to move large, heavy objects made of metal. In this lesson, you'll learn how electromagnets work. We rely on electromagnetism every day. Starting with number 1, click on the images in numerical order to learn more about electromagnetism. Magnets have magnetic fields, which are invisible but can be detected. You can see the magnetic field of a bar magnet if you lay compasses around the magnet. A wire can have magnetic properties if a current is present or if it has been magnetized. The interaction between electricity and magnetism is called electromagnetism. The electric current in a straight wire forms a magnetic field around the wire. A solenoid is a coil of wire with an electric current in it. Solenoids are found in many of the devices people use every day, including cars, washing machines, and other electrical appliances. What happens to the compasses when an electric current is in the solenoid? Because of electromagnetism, the solenoid has a magnetic field like a magnet does. Increasing the current in a solenoid increases the strength of the magnetic field around the solenoid. As shown here, a solenoid that is attached to a stronger battery affects compasses that are farther away. This is because it has a stronger magnetic field. The number of coils in a solenoid also affects the strength of the magnetic field around the solenoid. As you can see, a solenoid that has more coils produces a stronger magnetic field when an electric current is present. Remember that large electromagnet in the junkyard? An electromagnet is a solenoid that has a soft iron core. When an electric current is in the solenoid, the iron core becomes magnetized and makes the magnetic field much stronger. This makes it possible to use an electromagnet to lift thousands of pounds. When the electric current is turned off, the magnetic field disappears. How does a solenoid differ from an electromagnet? Type your response in the box. Click OK when you're done.
I always have to skip that.
Electromagnets are handy tools. One of the places they are most often used is in electric motors. An electric motor is a device that converts electrical energy to mechanical energy. Click play to learn more about how simple electric motors work. A simple electric motor has only a few parts: a magnet, a wire coil, an electric current source such as a battery, and an axle. This motor uses a simple wire loop instead of a coil with multiple turns. Note that the poles of the magnet are on opposite sides of the wire. This is what makes the motor work. The attracting and repelling forces between the poles and the wire loop cause the wire loop to turn. When the switch is closed, electric charges move through the coil in the magnetic field. The electric field of the coil interacts with the magnetic field of the magnets. As a result, the coil rotates, which also rotates the axle. The rotating axle has mechanical energy. So, electrical energy has been converted to mechanical energy. The direction of the current affects the direction in which the coil turns. If the current is reversed, the coil and axle turn in the opposite direction. You might not know it, but you use electromagnets every day. Click the images to learn about some of the devices that use electromagnets. Electromagnets can be used to move trains. These trains, called maglev trains, move more quickly than regular trains. Maglev trains move hundreds of kilometers per hour. Maglev trains are so fast because electromagnets suspend the train a small distance above the tracks. This reduces friction, making it possible for the train to move faster. Most stereo speakers work because of electromagnetism. The electrical energy passing through the electromagnet in a speaker is converted to sound energy, which you can hear. Many devices that have speakers, such as radios and cell phones, will have electromagnets. The electromagnet in a microwave oven produces microwaves, a type of electromagnetic energy. These microwaves heat food. A computer may have several electromagnets. These electromagnets can be found in the monitor, speakers, hard drive, and the fans that keep the computer cool. You can find electromagnets throughout an automobile, from electric motors to speakers. Power locks and the brake system are other places where electromagnets may be used in a car. A specialized use of electromagnets is in an MRI machine. MRI stands for magnetic resonance imaging. The powerful magnetic field produced by the electromagnets in an MRI machine can be used to produce images of the inside of the body. Doctors can use these images to diagnose and treat diseases. Which of these devices use electromagnets? Click the correct answers. Great job! The speakers of a stereo system contain electromagnets. You got it! You can find electromagnets throughout an automobile, from electric motors to speakers. That's not it. A light bulb may carry an electric current, but it doesn't contain any electromagnets. Correct. Computers have electromagnets in the monitor, speakers, hard drive, and fans that keep the computer cool. Computers, automobiles, and stereo systems all use electromagnets. Light bulbs don't contain electromagnets. You know that the movement of electric charges through a wire coil in an electric motor can produce a magnetic field, converting electrical energy to mechanical energy. But what happens to a wire when you move a magnet around it? Click the images to find out. The movement of a magnet can be used to induce or generate an electric current. Moving the magnet changes the magnetic field around the wire. The process of inducing a current in a circuit by changing magnetic field is called electromagnetic induction. The galvanometers shown measure the change in current. Notice that moving the magnet produces a current. In electromagnetic induction, mechanical energy is converted into electrical energy. A device that uses electromagnetic induction to convert mechanical energy into electrical energy is called an electric generator. Shown here is a very simple electric generator. When the wire coil is moved in the magnetic field, an electric current is induced, making it possible to power the light bulb. Electric generators convert mechanical energy into electrical energy. This mechanical energy may come from coal, gas, water, wind, or other sources. Electric generators vary in size from very small to the huge generators that can be found in hydroelectric dams. A small generator can be used to keep the lights on in your house after a power outage. Larger generators provide electricity for entire cities. Let's look at motors and generators side by side. Recall that both have magnets and wire coils, and they rely on the interactions between electricity and magnetism to work. But one uses electrical energy while the other produces electrical energy. Click the images to compare them further. An electric motor converts electrical energy into mechanical energy. The electric current in the wire coil in an electric motor causes the coil to rotate within the magnetic field. A very simple electric motor is shown here. When an electric current is in the wire coil in the magnetic field, the coil turns. So, electrical energy is converted into mechanical energy. An electric generator does the opposite of what an electric motor does. It converts mechanical energy into electrical energy. In an electric generator, the rotation of a wire coil within a magnetic field produces electric current. This is known as electromagnetic induction. In electric generators, mechanical energy from an outside source causes the coil to turn in a magnetic field. This produces an electric current in the coil. We're surrounded by electric motors and electric generators. We're surrounded by electric motors and electric generators. Look at the devices pictured here. Which ones contain electric motors and which contain electric generators? Drag each item to the correct box. You
So if
can
we were
click the images to find out what they are.
If we were in class, you'd be able to come to the board and drag your answer to the correct section here, either electric generator or electric motor.
Good job! Hydroelectric dams, wind turbines, and power plants all use electric generators to convert mechanical energy into electrical energy. Power tools, electric fans, and many trains rely on electric motors to convert electrical energy into mechanical energy to produce motion. Electricity reaches your home as an alternating current, which means the current periodically reverses direction. Power lines carry a high voltage electric current. The voltage of the current needs to be decreased before it enters your home. The device that decreases the voltage in an alternating current is called a transformer. Electromagnets inside transformers change the magnetic field, decreasing the strength of the current. Other transformers can increase the voltage of a current. A transformer increases or decreases the voltage of alternating current. A simple transformer is made up of two coils of wire wrapped around a square-shaped or circular iron ring. The primary coil gets alternating current from an electrical energy source. When a current is present, the iron ring is an electromagnet. But remember, the current in the primary coil is alternating. So the magnetic field of the electromagnet changes as the direction of the current changes. The changing magnetic field in the iron ring induces a current in the secondary coil. Click the highlighted areas to learn more about transformers. A step-up transformer has a primary coil with fewer loops than the secondary coil has. In the step-up transformer shown, the primary coil has 9 loops and a voltage of 100 volts. Note the greater number of loops in the secondary coil of a step-up transformer. In this step-up transformer, the secondary coil has 18 loops, which is twice as many as in the primary coil. In a transformer, for each coil, the voltage divided by the number of loops must be equal. So, 100 volts divided by 9 loops multiplied by 18 loops equals 200 volts in the secondary coil. In a step-down transformer, the primary coil has more loops than the secondary coil has. In this step-down transformer, there are twice as many loops in the primary coil. The primary coil of this step-down transformer has 18 loops and a voltage of 1000 volts, and the secondary coil has 9 loops. What is the voltage of the secondary coil? Well, 1000 volts divided by 18 loops multiplied by 9 loops equals 500 volts in the secondary coil. Let's review what you've learned about transformers. Drag each label to the image it describes. You can click the images to find out what they are. Great job! A step-up transformer increases the voltage of a current. It has more loops in the secondary coil, which is where current is induced by the changing magnetic field in the iron ring. A step-down transformer decreases the voltage of the current. It has more turns in the primary coil. The primary coil gets alternating current from an electrical power source. In this lesson, you learned that an electric current in a wire can create a magnetic field. Which of these items produce a magnetic field when an electric current is present? You can roll over the images to find out what they are. You got it! A transformer contains an electromagnet, which produces a magnetic field when an alternating current is in its primary coil. That's right! An electromagnet is a solenoid that has an iron core. The core becomes magnetized when an electric current is in the solenoid. You got it. When an electric current is in a solenoid, a magnetic field is produced. Correct. An electric motor contains an electromagnet, which produces a magnetic field when an electric current exists. All four choices are correct. Solenoids, electric motors, electromagnets, and transformers all produce magnetic fields when an electric current is present. Transformers change the voltage of a current. The image below shows an electromagnet from a transformer. Drag the labels to the correct parts of the transformer shown. Great job! The electromagnet in a transformer usually has a circular or square-shaped iron ring and two coils. The primary coil, which gets alternating current from an electrical energy source, and the secondary coil, where current is induced by the changing magnetic field in the iron ring. In the step-up transformer shown, the secondary coil has twice as many loops as the primary coil has. The voltage between the coils doubles from 3,000 volts to 6,000 volts. You've learned a lot about electromagnetism. Let's review the main ideas from the lesson. Electromagnetism is the interaction between electricity and magnetism. When an electric current is in a coiled wire called a solenoid, the solenoid has a magnetic field. An electromagnet is a solenoid that has an iron core. When current is in the wire, the core becomes magnetized, giving an electromagnet a much stronger magnetic field than a solenoid alone. Changing the magnetic field around a wire can produce an electric current. This process is known as electromagnetic induction. Electromagnets are used in electric motors, which convert electrical energy into mechanical energy. Electric motors can be found in power tools, kitchen appliances, and many other devices. Electric generators convert mechanical energy into electrical energy. They vary in size from the tiny generator in a hand-cranked flashlight to the giant generators in hydroelectric dams and power plants. Transformers use electromagnets to increase or decrease the voltage of an electric current. The electromagnets in transformers have iron rings that are usually circular or square with two wire coils. Step-up transformers increase voltage, while step-down transformers decrease voltage. Now that you've finished this lesson, if you wish, you can go back and review any part of the lesson again.
After this lesson, you're going to go into BrainPop and type in electromagnets. You can click right here to electromagnets. I'm going to have you watch the movie and then take the graded quiz. And after you've taken the graded quiz, you can email me your results. If you look at your learning plan, on Wednesday, you'll be directed to go into SOL Pass. So go to middle school, physical science, electromagnetism. There are different activities for you here to practice. Your learning plan, again, that I emailed to your parents on Monday has, again, the plans for each day. Your login information is also provided. It was in packet 3. If you do have any problems signing into BrainPop or into SOL Pass, please let me know. You can email me here at heidi.younger@centralhealth.com. I can email a response back to you, or I can give you a call. I hope you have a great day. Again, try your best, and I will talk to you soon.